Okay. So any questions? Okay, last time we've been starting to talk about the Chinese remainder theorem, which says that if you take a set of co-number or of co-prime natural numbers, okay, and you take also a corresponding set of remainders. I mean, each AI is modulo MI. So there is a unique solution to the obtained system of equalities. I mean, there is a single X modulo M, which M is the product of all the MI. Okay, there is a single X such that modulo M1 will be A1, modulo M2 will be A2, and etc. We said, I mean, tell us our remainders, and we are going to tell you who you are. Okay. So the way to find X is actually the proof of this theorem. So we said we are going to construct a basis. Each element in the basis, I mean, EI is such that, I mean, it's a number such that modulo other MJ is 0 and modulo MI is 1. And now the construction of the basis is before we know something about the remainders. It has nothing to do with the remainders. It only has to do with the numbers, which are co-prime. And once you establish such a basis, then using the remainders, it's like some combination. I mean, you take A1 times E1 and etc. Then this will be X. Why? Because X modulo M2 is just A2, because E1 modulo E2 is 0 and all others E are 0 modulo E2. The only one which is 1 is E2, so you remain with A2 and etc. So this solution is the unique solution of the system modulo the multiplication M. So now we are going to see how do we construct this basis. Okay, so this is what we want. We want to find natural numbers. Each EI modulo MI is 1 and modulo MJ is 0. So how do we construct that? Okay. We take NI to be M modulo MI. Okay, M is the multiplication of all. Okay, and you divide it by MI. So what do we get? We get a number which contains all others MJ except for this MI. So first, we know now that NI is co-prime to MI, because we have divided. I mean, NI is after you take off MI from M. So in this number, you don't have any prime which exists in MI, okay? Because all others are co-prime to MI. So here, it is co-prime to MI. So if it is co-prime to MI, as we have learned last time, you can find an integral combination. Let's call it SI and RI. This is true for any I, of course. Such that SI NI plus RI MI is 1. Okay, we have said last time that if you have, I mean, this is true not only for 1. If you have GCD-D, this is Euclides. If you have GCD-D, then you can find an integral combination which gives you this D. So in particular, also 1. And now we are going to call this number, we are going to call it EI. Now, only for us to remember, I mean, it's like you are reading Sini, which is Chinese in Hebrew. Okay, so this is how I remember. Okay, so this is going to be EI. Why is it? I mean, it satisfied this thing. Why? Because EI modulo MI. I mean, all this is 0 modulo MI, so it's 1. So EI modulo MY it's 1. And since NI contains MJ to any other J, okay, so this is 0 modulo MJ. Okay, so this is how we construct this EI. So until now, okay, we've seen how to construct the solution, how to find it. But how do we know that this is unique? Okay, so until now, it's existence of the solution. About the uniqueness, so we say, suppose Y is also a solution. So also Y satisfies this system. I mean, Y minus, Y, each MI divides Y minus A1. I mean, if you take off the remainder, you get a multiplication of M1 of M1 and etc. I mean, okay, MI divides all Y minus AY, but all these are coprimes. This is given. So if you have a coprime numbers that divides this number, so also the multiplication divides. Each one. Just a minute. What I wanted to say. Sorry. I want to say the following. I want to say that m divides y minus 6, because this is true also for x, of course. Okay. So if all these divides both this one and this one, so m divides the gap. Okay. And this means actually that they are equivalent modulo m. So modulo m, you have only one solution. I mean, of course, you can take infinitely many. You have infinitely many solutions. If you find one solution, then you add m, you have another. But in the range of 0 to m minus 1, you have only one. Okay. Let us see an example. Okay, find the solution to this system. Okay, so the first thing we must verify is that these MIs are coprime, which is immediate in this case. Okay. So, I mean, okay. So now let us construct the basis. Okay, it has nothing to do with 1, 2, 3. So how do we do that? We say our M is say 60, 420. And now we can write some table. Okay, so we have MI. MI is 4, 7, 15. We have NI, which is the multiplication of the others. So here you have 105. Here you have 16. And here we have 28. And now we want to find EI. Okay, so So since these are co-prime, we can find, I mean, there is an integral combination of both that gives you 1. That's all. Okay. So in other words, so who is our Cine here? What is our Cine here? What is E1?
0.
105.
Oh.
Because this one is modulo the others. I mean, modulo, just a minute. No. Yes, okay. This is our S1 N1. Okay. Okay, this is E1. Let us check it. 105 modulo 4 is 1. Modulo 7 is, what is modulo 7? You have 70 and this 0, and modulo 15 is 0. Okay. Now let's go further. We look at this. This is how we find the coefficients. Okay. So here we have minus 16 and here minus 1. So it's minus 17. Let me check it is correct. So I'm doing 120 minus. Yes. Okay, so if our N2 was 16, so this is our Cine. Let us check. 120 modulo 7. Okay, so you have 17 and 49. Yes, it's 1. And these two are 0. Okay. Now, if you happen to get here something negative, then you take a positive representative. I mean, you add 420. Okay, this is the basis should be here, the basis. Okay, so let's do the same thing for the third one. So we have this. Let me check. It is correct. Please stop me if something is not clear. Okay. So now we have so this is actually the queen. So let us write this. Three. Okay. So who is our Cine here? It is this one. Now, how much is it? Okay. So now we have constructed the basis. So the only thing that remains to do is find x. We had 1, 2, and 3. So it's 1 time 105 plus 2 times 120 plus 3 times. And now, of course, we take the least representative. I mean, we remove 420 from this. So how do we, what do we get? Okay. So I remove twice. I mean, 840, and this is the solution. Okay, so this is x. Let us check. 93 modulo 4 is 1. 93 modulo 7 is 2. And 93 modulo 15 is 3. Now, you may say, okay, it's a long computation. Maybe I couldn't find it more quickly. So think about greater numbers, okay? It's not so simply. So this is the how we find the solution. And there is a unique one. I mean, if we take I mean, this is also a solution. Every 420, you have another solution. I mean, you take 93, you add 420, you get another solution, etc. Okay. We are going to see later how all this material, gets into, how all it is gathered together. Okay. So let us talk now about homomorphism. Okay. So what is the homomorphism? Actually, we have been talking about, we called it operation preserving, but the correct name is homomorphism. I mean, it has the same structure, homomorphism. Okay. So what is homomorphism definition? A map between monoids I remind you that monoid is first, a system with operation which is well defined, closed, and also it's a semi-group. It has the associative rule, and also it has a neutral element with respect to this operation, but not all elements are necessarily invertible. This is a monoid. It's one step before a group. If you take the group of this, the invertible, you will get a group. So what is a morphism? A map between monoids, okay, is a homomorphism of monoids if it preserved the operation. Which means that to any AB in G, phi of A dot B, whatever this operation is equal to, if we first take the image of phi A and then we do the operation in H with phi B. Okay, so this is the definition. We have seen it before. Now, if furthermore after being homomorphism, if phi is injective, okay, so we call it, then phi is what we call it monomorphism.
Can you please clarify what is the dot before the phi at the start?
It's just the bullet. Okay.
Okay.
Because we are going to have others.
Sure. Thanks.
If phi, furthermore, now I mean this is okay, this is a different properties. If phi is subjective, what we call al, so homomorphism subjective, we call it epimorphism. And if it is both injective and subjective, then phi is isomorphism. Okay, so let us see examples.
So, just a general question.
Mhm.
So in order to have a function to be homomorphic or homomorphism, you must have the associative and neutral associative rule and neutral elements, even if we are not talking about algebraic structures. I don't know, some type of other creature.
You are asking whether we can relate this notion to structures that are not monoids.
Right.
I don't know.
Okay, thanks.
I'm not sure it has any significance. But anyway, in our course, we only refer to semi-groups.
Sure,
maybe I don't know. Maybe. Okay, examples. The first one, phi from z to z. Now, if I'm writing only z without the operation, and I treat it as a group, so it, of course, the addition. So phi takes x to 2x or 3x. So first we have to check it is homomorphism. Of course, phi of x plus y, which is by definition 2 times x plus y, it's like 2x plus 2y, which is phi x plus phi y. So it's homomorphism. Now, is it injective? Yes, because you cannot have two elements in the origin that goes to the same image. Okay, so it is injective. If x is different than y, then of course 2x will be different than 2y. So it's a mono. Now, is it surjective? The answer is
no.
No, because you only cover the even numbers, not the odd ones. Okay. the image of phi is 2z. Okay, so phi is a monomorphism.
Sorry. Can you just tell what is injective and surjective?
I mean, injective, I mean that two distinct origin get two distinct image. Okay, for example, this function, okay, from R to R is not injective because both +3 and -3 goes to 9. They share the same image. So no, this is not injective.
Okay.
Okay.
Yeah.
But here, of course, if the origin are different, so also their image are different. Okay, this is first example. Now, second, suppose you take U10. I remind you what is U. It's the order group, which its element is the numbers until 9 that are co-prime to 10. So here it is 1, 3, 1, 3, 7, and 9. With multiplication modulo 10. This is U10. And now I'm looking on the map from U10 to its subgroup generated by 9. Okay, which is actually a subgroup, a proper subgroup. It contains only 1 and 9. Why 1 and 9? Because 9 in the power of 2 will be again 1. So this is a subgroup. Okay, so now I defined phi to take x to its square. Is it a homomorphism? The answer is yes. Why it is homomorphism? Because phi of x multiplied with y, these are only two representative of these classes. I mean, each one is a class. Okay, so it will be xy squared, which is xy. Now, this group is commutative, abelian. So it's like writing, because it's just multiplication. So it's actually phi x, phi y. Okay. Of course, it's subjective. Why subjective? You only have to find an origin here that covers, of course, 1 goes to 1. And how do I cover 9? By 3. Okay, so it is subjective. Of course, it cannot be injective. Why it cannot be injective? Because you go from 4 elements to just 2. So of course you have a non-trivial kernel here. I mean, you must have, yes, we call it in Hebrew shovach yonim. I mean, you must have here elements that goes to the same image. For example, what? What will be an example? phi of 9, it's like, because 9 square is 1, it's like phi 1. Okay, so it's not injective. We have the same image for distinct sources. So actually it's epimorphism. Now, as you can see, this was homomorphism only due to the fact that the group was commutative. But in general, taking an input, taking its square is not homomorphism, okay? For example, if I take GL2 to GL2, by taking a matrix to its square, then it's not homomorphism. Because phi of AB will be AB, AB, which is not equal in general to A square, B square. Okay, it's not an homomorphism if the group is not abelian. Okay, and the last example we have seen before, you take from R with, I mean, this is all real numbers with addition to only the positive one with multiplication. How do you do that? For example, you define x goes to 2 of the power in x. So we have seen that this is the usual way to pass from addition to multiplication. In the other direction, it will be logarithm. So why is it homomorphism? Because phi of xy is no, the action here is plus. So since it's associative, you see why I don't think I mean your question, if it's not the same group, I mean I don't see, I mean any significance in this definition. Okay, so here it's phi x, phi y. So we passed from plus to multiplication. Okay, so this is homomorphism. And of course, since I mean it grows, I mean it goes up, it's monotone, so it's injective. Of course, it is surjective. I mean, you can always take the logarithm. It is surjective. So actually, phi is isomorphism. Okay. For example, any linear transformation, like in linear algebra, okay? Any linear transformation is homomorphism. It has, of course, no reason to be injective or surjective, but is any linear, because let us see this example. If I take, for example, a linear transformation, from say Rn, so of course it's together with the addition of vectors. How do you define such a thing? Using a matrix. Okay, so here you put your vector, so it is a matrix like this. Okay, and then you get a vector here. So any matrix M on N is a transformation from Rn to Rm. Of course, it is, I mean, phi of V will be AV. Okay, this is V. Okay, so of course, this will be homomorphism because this is, I mean, now we see that it's only a particular case of homomorphism because phi of V plus U, of course, it's, I mean, this is the definition of a linear transformation. Okay, so in general, it has no reason to be surjective or injective, but is, of course, homomorphism. Now, as we have seen in linear algebra, now it is more general. We have this claim. Given a homomorphism of monoids, like we've seen, monoids okay, then of course phi of the neutral element G must, I mean, the image of the neutral element must be the neutral element in H. And two, if you take an invertible element, okay, so phi of its inverse, it's like taking phi and then taking inverse. I mean, if you start with an invertible element of G, this is group G, okay? So its inverse, it's like taking first X and then doing the inverse. Why is it true? Proof. So for the first property, we have seen like this in linear algebra, because phi of 1G is like phi of 1G multiplied with 1G, because one doesn't do anything, it's neutral, but it is homomorphism. So it's phi of 1G squared. Now, how can we, I mean, we can, I mean, multiply these both sides by the inverse, but we can also understand that if you have an element that is equal to its square, then it must be the neutral in the target. Okay, this was one. For two, you do something similar. I mean, you start with 1H. And as we have seen, it must be an image of 1G. Now, instead of writing 1G, you write it like X multiplied with its inverse. Of course, we refer to invertible element. Now, since it's homomorphism, now we have seen, now we see that the element which takes in H phi x back to 1 is this element. So it must be the inverse of this. Okay, because this is the inverse of phi x if it takes it to 1. Okay. The importance of the second properties is that if we start, so corollary, I don't remember if, if you need two L's, okay? So if you have started by G and H, okay, was G and was H. Suppose these are the invertible ones. So you can be sure that if this is F, if this is phi, then if you reduce yourself, if you restrict yourself to this input, so the image will be inside here. I mean, not necessarily covering, but here inside. Because any element which is invertible will remain invertible in the target. You see, this is an invertible element. So if we started with an invertible element in the source, its image will be invertible in the target. Okay, so image phi of group is inside a group of H. And in particular, if phi is isomorphism of monoids, then of course this remains true in the groups. We are going to use it. Okay, so if you restrict yourself, if the original phi is in isomorphism, okay, so you know that any two distinct sources are going to distinct images, okay, and it covers all H, then the invertible must be isomorphism to the group of H. Okay. So now we want to define a new structure. Maybe you have heard about it. It's called a ring. Have you heard about a ring? For example, a field is a special case of a ring. Okay, so what is a ring? So a ring is an algebraic structure. With two R is the set of elements with two operations, not one, two operations called or denoted by plus and multiplication. Now, it doesn't have to be the original plus and the original multiplication. It depends on the ring, but this is the notation of the two operations, such that now we have three conditions. The first one is that if we take the elements of R together with the plus, it's an abelian group. If you take R with the what we call it, what we denote by dot, then it is a monoid. And if we take, and the first thing is that you must satisfy the distribution law. Which means that any free element in R x dot y plus z is like x dot z plus x dot y plus x dot z, and also in the other direction. So if this is satisfied with the two other properties, when we call it a ring. So you see that with respect to the what we call dot, doesn't have to be a group, only a monoid. Can you think of an example?
Just a question.
Yes.
First, what is ring in Hebrew?
Chug.
Okay. And the second, what is reason after distribution? Satisfying
Low.
the
Low.
low. Okay.
So can you think about examples of rings?
Matrices.
Okay. Matrices from what order? Any order? No, you cannot have any order because any order is okay with plus, but it's not okay with multiplication. So take it, for example, Mn over some field F, okay, with usual addition and multiplication. So with respect to plus, of course, it's a abelian group because any, of course, plus is abelian. I mean, A plus B is B plus A. And any matrix, its inverse is minus, okay? Okay, but with respect to the multiplication, it's not a group. I mean, you need the determinant to be not equal to 0 and doesn't have to be. So this is and of course, it's not abelian with respect to multiplication. So this is very good. This is an example of a ring, but a more basic example, the most basic example, we call it the initial object. Okay, so with respect to the plus, it's an abelian group. I mean, the inverse of 5 is -5, but it's not a group with respect to dots. Okay. For example, the ring of a polynomial over, say, over R. Together with plus n dot. So why is it an abelian group with respect to plus? Because any polynomial, you take its minus. Okay. But I mean, you have, in fact, the inverse here are just the scalars, because this is not a polynomial. Okay, this is not. I mean, this does not belong. Okay, so the only invertible elements here, okay, are the scalars which are not 0. But it's a ring. Now, if in addition, okay, if, okay, given a ring, of course, you have many more examples, like you can take functions with composition and etc. Given a ring such that if you take out the 0, so together with multiplication, it's a abelian group. If this is true, then how do we call it? How do we call such a ring that if we take off the 0, so with respect to plus, it's an abelian group? How do we call it in linear algebra? How do we call it? Then it is field. This is definition of a field. Okay, a field is a ring such that if you remove the 0, and now you have to know what is 0. What is the definition of 0? For example, if you have matrices in general, what we call 0? What is 0? I mean, it cannot be the usual scalar because it can be many things. I mean, the ring.
The neutral element
With respect to
the group.
With respect to what we called plus.
Yeah, the operation, yeah.
Okay, because we have two operations. The one you denote by plus and the other multiplication. It doesn't have to be the usual ones. So 0 is by definition the neutral element with respect to what you call plus. Okay, so example to fields, of course, we know Q, R, C, and okay, these are fields. But we are going to see later that we have also finite fields, which will be the platform, the basic platform to cryptography, finite fields. Okay, these of course are infinite. Okay. Are there any questions so far? RL, you are with us?
Yes, I'm with you.
Okay. So now we are going to take things together. Okay, claim. I claim that given two natural numbers, if they are coprimes, then the cyclic group ZNM is isomorphic to Zn direct product with Zm. Okay. Now I want to remind you, what is Znm? If I don't write the operation, it's the usual plus modulo. So here it's plus modulo Nm. I mean, any Zn is cyclic because one is a generator. So this is also cyclic and this is also cyclic. But in general, the direct product of two such groups has no reason to be cyclic. For example, Z2 with Z2 is not cyclic. Okay, more explicitly, if, and we are going to see later, if and only if these are coprimes, then their direct product, what is direct product? These are pairs, okay? A psic B, the first component belongs to Zn and the second to Zm. So this is, in other words, this group is cyclic with, I mean, in any case, you have Nm elements here and Nm elements here. This is true anyway, because you have Nm combinations of A psic B. So once you have Nm elements, the only, I mean, and this is cyclic. So if this is also cyclic, then they are isomorphic. Because think about the table of multiplication. I mean, you just take one generator and all the elements are just powers of this generator. So it doesn't matter how do you call it. So you have only one cyclic group of a given order. So the question is whether is it cyclic or not. Okay, if it is cyclic, then it will be isomorphic to Znm, which means that they will have the same multiplication table. But let us go.
Can you please write that? Yeah, I understood what you said, but I'm not sure I will remember it afterwards.
Okay, I prefer to show it, okay, in the usual way, okay,
Sure.
because we haven't proved it yet. What I just said, we are going to prove it. We are going to see that given a number of elements in a group, you have only one cyclic group up to isomorphism, okay? But we are going to see that. So for now, we don't rely on it. I'm going to prove it by the definition we have seen. Okay. And this is a morphism of rings. Because each such object is considered as a ring. Sorry, I didn't write it. This is a ring. Of course, with respect to multiplication, it has no reason, it is not a group. But with respect to plus, it's an abelian group. So this is, it's not only isomorphism of groups with respect to plus. It's more powerful. I mean, it's a isomorphism of rings. What do I mean by isomorphism of rings? I mean that we can find an isomorphism which is both. Let me write it, okay? There is a homomorphism phi, okay, which is both iso of okay. So it is the morphism of both of this group and these monoids. Okay. So how do I prove it? Okay, don't be worried. I mean, don't worry. This is very simple. Because first we have to show that it is homomorphism with respect to both operations. Okay. Now, sorry, we didn't define any map. So now I'm going to see you. I'm going to show you the map. Okay. Phi of x will be x modulo n, psic x modulo m. You take an element here and you find its remainder modulo n and modulo m. Why do you think such a map is both injective and surjective? I mean, without speaking about the operation, why is such a map is both injective and surjective? Why do you think it's so?
The number of elements is equal, no, in both.
Yes, but if it's not injective, I mean, if you have 2x here,
Yeah,
that
right.
both, then it won't be neither injective nor surjective. So why do you think it is true that such a map is both injective and surjective? I mean, of course, if one, then the other is true. I mean, if it's injective, it must be surjective because it's finite sets. But why is it injective? Why do you say it? I mean, I'm asking you because you can think about why it is true. Why do we have a single x given the remainders modulo n and modulo m?
Yeah, it divides both.
Yes,
It
these
must-
are core primes.
Yeah.
So why is it injective?
Maybe it's from the Chinese remainders.
Exactly. This is a Chinese remainder theorem. This is what it tells you. That once you have the elements here, you have a unique solution. You have a solution, this is why it is surjective. To any element in the target, you have a solution. So it's surjective. And this solution is unique, modulo nm. Exactly. And m, this is what we called m, because it's like m1 and m2. Okay. Now, it's not hard to show that this is homomorphism with plus and multiplication, okay? For example, phi of x plus y is x plus y modulo n psi. Okay, and the same for multiplication. This is, by the way, phi of x plus phi of y. Okay. Why do we need that? This is very powerful. We're going to see how do we use it in cryptography, okay? This claim. But for now, let us define another object, which is called the Euler function. Given n, natural number, okay? Then the Euler function I mean, I shouldn't have to start with this whole thing. Okay, the Euler function, sorry, okay, the Euler function is phi from n to n. Phi of n is the number of elements in the Euler group. Okay, this is the definition. Okay, this is the I mean, let us give him more credit. Okay, he doesn't need our credit. For example, what is phi of 6? Is actually the number of coprime elements until 6. It's the order of this set. Which is 2. What is phi of 8? It's the cardinality of this set. It's 4. Okay. Now, of course, if P is a prime, then what will be phi of P? If P is a prime number, so what will be phi of P? I mean,
P minus 1.
P minus 1. Okay. So okay. And what is PK? So in order to answer this, okay, what are the numbers that are not coprime? I mean, which have some mutual divisor. The answer is what is the answer? I mean, one it's not. I mean, one is a coprime. So we have P, 2P, 3P. I mean, anything. I mean, you must have P, even in some power. I mean, the last number which can be considered is P in order of a power K1 of P. So how many elements you have here? You have P in K minus 1. I mean, you can count them 1, 2, 3 until this one. So if you remove these, you get that PK is actually all the possible number until PK minus PK minus 1. Okay, for example, what is phi of 8? This is actually phi of 2 in the power of 3. So it is 2 in the power of 3 minus 2 in the power of 2. Okay, which is 4. How many numbers you have coprime to 81? So it is 9, 2 minus 9. Okay, which is 72. Now, the last thing we're going to see is the prototype of what we have seen so far. I claim that if N and M are co-prime, then phi of n m is phi n phi m. Proof.
Can you stop a bit about the phi of 81? It doesn't supposed to be 3 in the power of 4.
You are right. Thank you. Thank you. Thank you. Sorry. Of course, you take P. You are right. I'm sorry. You are right. I'm sorry. Thank you very much. Okay. Why is it true, this claim?
Just to be clear, so you needed to take the minimal prime number in order to do the
Yes,
calculation?
because this formula, okay, it's for prime.
Yeah, okay. It's so if there are several prime numbers that make
Oh,
up a number.
so you use this one. I mean, if you have a very general number, you first take its composition to primes. Okay, you distinct them, and then to each prime you take this formula.
Okay, cool.
Okay, but why is it true? Okay, because what is P and M? It's the order of U and M. But what is U and M? U and M is the group with respect to multiplication of Z and M. Okay, but if you think about this monoid without the group, this monoid is isomorphic, as we've seen, to Zn product with Zm. Because if you have the map that we have defined above, which is a map of injective and subjective, okay? So these are isomorphic. Also with respect to multiplication. Now, if you have two components, so the group of this direct product is actually the group of the first one. This is a usual multiplication. Which is actually the cardinality of N and M. Okay, so you see how we combine all the things that we have seen. Because you have first isomorphism of monoids, but if you remember, once you have isomorphism of monoids, then this also true to the restriction to the invertible ones. You remember, we've seen that? Okay. So once we have seen isomorphism of these monoids, this is true also for the groups. So this is why this cardinality is equal. Of course, without the group, it's true. It's also NM. But the invertible of ZNM correspond to invertible of this product. And then you find this guarantee, okay? So just one example. For example, phi of, I don't know, so we can think about 18, I mean, 9 is 2, okay? And we can think about 5 and 2, this is true? No, you have such thing, isn't it? Okay? So now you say this. Is it true? 6, 24, 8, 28. Okay, 9 and 20 is okay. You see what I've done here? The path from here to here is our last claim, and inside you have prime. Okay, so this is how we do it. Okay, guys. So I must leave here. Thank you for listening. And if you have any question, please ask me with the WhatsApp or the mail, okay?
Sure, thanks.
So thank you and see you next week.
Thank you.